Welcome back, everybody, and welcome to a new topic and the second project and the last part of the semester. We are going to focus on, since there was a good fraction of you who wanted to work on neural networks and Boltzmann machines and deep learning, we are going to focus on these techniques for solving project number 2 for the rest of the semester. The main topic, which will keep us busy now, is basically today, first an introduction to deep learning methods and what they stand for. And then we are going to look at a class of deep learning methods, which are called generative methods, which leads us to the introduction of Boltzmann machines. And I will try to give you the reason why we are going to focus on that type of deep learning architecture and method in the beginning. And then we will, towards the end of next week, the beginning of the week thereafter, we will also explore how we can actually use neural networks. And I will try to build up a kind of understanding for why we use these methods and why we use explicitly Boltzmann machines in the beginning. So the basic idea is now to end the rest of the semester with lectures on these topics. And what you will also see if you now go to the University of Oslo, the official website for Physics 4411, you will see now that I've put up a tentative schedule for the rest of the semester. So today we are going to look at essentially Boltzmann machines, and we will try to wrap that up next week together with a start of discussion on neural networks. And we will continue with that on till May the 4th. And May the 11th will be our last session. And the rest of the time will be dedicated to just project work. And we can have additional lab sessions towards the end of the month if that is needed or wanted. So this is basically the plan for the rest of the semester. So we will have essentially 3 lectures which will cover the topics which we need. Going back to the material which we will cover today, there's a reason for why we are going to look at Boltzmann machines first. And one of the main reasons is that this is the simplest method to implement with respect to what you have developed already. So it means that the program which you have taken is a program which you can easily extend upon by replacing the wave function with a totally new ansatz. And there is a program at the end of the lecture notes for this week, and which we are going to look at. So we're going to take a mix of a detailed derivation of things and a top-down approach, where you can look at how you can implement the Boltzmann machines in a simple Python program. And then hopefully that gives you enough guidance so that you can, if you wish to program in Python, you can use that. If you wish to program in C++, you can see how you can actually build in these details into your program. Okay, so as we said, the alternatives for project 2, we have a fermion variational Monte Carlo, which is essentially a continuation of project 1. And deep learning apply to what you have developed in project 1, except that we can change the physical system. You should feel free there to define the physical system you would like to explore. And in this specific case, we are going mainly to look at Boltzmann machines first, and then we are going to move over to the implementation of neural networks. I put the implementation of neural networks in the project description as something which is complementary or optional. And the reason for that is that the Boltzmann machines, historically, there was a paper by a guy called Giuseppe Carleo and Michael Troyer, which presented the first applications of these deep learning methods on the quantum mechanical easing model and other spin type of models. And then they used Boltzmann machines. Now, Boltzmann machines are not that flexible as neural networks, but they're easier to implement. And that's why we, from a pedagogical point of view, we start with Boltzmann machines, and then we will move over to neural networks. So there are several reasons for why we start with Boltzmann machines. And one of the reasons is the pedagogical one, and the other one is also a historical one, that these were methods which have been used by people as the first types of calculations of deep learning methods applied to quantum mechanical systems. And they also link well with a kind of way we think as physicists, because we're going to use a Boltzmann distribution as an ansatz for a trial wave function. Then there are also other variants. There's a quantum computing variant. We have many-body methods like copper cluster theory, and there's also time-dependent Hartree-Fock project. But what we need to look at now is the basics of neural networks or deep learning methods. And then we are going to look at first at the mathematics of Boltzmann machines. And I will try to guide you through the basic steps there, so that you see the overarching topics first, and then we can still take a top-down approach and look at the code, and then we go back to the details. So I hope that can work as a way to get you started. Okay, so very quickly, if we now look at these Boltzmann machines, we distinguish between two types of deep learning approaches. One is normally called a discriminative method. They are mainly supervised ones, like a neural network. And there are tasks which cannot be done, like drawing new examples from an unknown probability distribution. So if you think of the trial wave function, the trial wave function is something which defines a probability distribution. Generative model, they generate the input again and again. They normally lead to what's called unsupervised learning. And they often have a probability distribution as a parameterization. And this probability distribution is the one which we use to actually generate new data. So Boltzmann machines were historically actually used in imaging. And before convolutional neural networks really replaced Boltzmann machines, they were seen as a viable approach for using deep learning methods to imaging. Now, the benefit for us is that we can use all the Monte Carlo machinery. We can use the gradient descent-based learning procedures for minimizing the cost function. And these energy-based models, they actually don't use backpropagation and automatic differentiation for computing gradients. Instead, we're actually using the machinery of Markov chain Monte Carlo methods. So if we then look at the neural networks, they normally have many, many hidden layers, whereas a restricted Boltzmann machine has only one hidden layer. You can stack them on top of each other, but the Boltzmann machines are easier to implement. So, as I mentioned in the very beginning here, there are some pedagogical reasons for why we focus on Boltzmann machines first. And also, they belong to a class of deep learning methods, which are extremely popular if you're thinking of something like variational autoencoders and generative adversarial neural networks. So the basic philosophy which you have with a Boltzmann machine is something which then is used in these very popular methods for unsupervised learning. Now, what I need to do now is, however, to set up some basic overarching themes so that you can follow a little bit of the kind of language which I'm using. I am partly assuming that you guys have had or have followed a course on deep learning or know something about neural networks, but I'm going to try to repeat some of the basic arguments here so that we are on the same level and then can appreciate a little bit better some of the technicalities which are to come here. So what I'm going to do now, after these introductory words, I'm going to go back to the whiteboard and I will try to outline the basic philosophies and the basic mathematics which is needed for this part of the project. And as I said, the using Boltzmann machines means that we can essentially take everything which we did in project 1 and reuse our gradient descent solver for finding the optimal parameters. We can use the Markov chain Monte Carlo method, which we have developed for finding the variational expectation value of the energy. And we can also use, again, when we have performed the calculations, we can use something like a blocking method to compute the expectation value of the variance, and then thereafter obtain a standard deviation. So as you will see, the only thing which we are going to change actually is the trial wave function and the way we set up the parameters. So that's going to hopefully be something which allows you to jumpstart with project number 2. And then we can go back a little bit later to neural networks. In case you want to do that, as I said, this is an optional part of project number 2, which means in turn that if you don't have time to it, I mean, there is no penalty in just staying with Boltzmann machines. However, if you want to use neural networks, there are some additional things to think of. Any questions so far, folks? Things which may be unclear or other things you'd like to ask about the projects? So just a quick reminder about the projects which we have. So the lectures will mainly focus now on deep learning methods. Okay, if there are no questions, I'm actually going to try now to bring in first the kind of overarching view of what we are going to do. And then we are going to dive into the details. Okay, so let's switch to the whiteboard. So I will assume that you guys have some knowledge of deep learning methods. So let me try to set up some central points first. So when we look at deep learning, as I mentioned, there are two basic lines of approach. So one is what is normally called a discriminative model. Discriminative approach. And this is often used with the supervised learning. So that means that you have labeled data. And you want the model or the specific method, like a neural network or convolution neural network or a recurrent neural network, you want they to be trained so that they can reproduce the data which you have, and then be able to make predictions based on that. And then we have so-called generative model. So in here we would have NN. This is going to be my acronym for neural networks, CNNs, convolutional neural networks. We have recurrent neural networks and autoencoders, etc. Autoencoders fall more under the category of unsupervised learning methods. And then we have so-called generative methods. And Boltzmann machines fall under this category. So this is mainly used with unsupervised learning. So we have, in principle, we have unlabeled data. These are often also called energy-based models, because the Boltzmann distribution has something which is given in terms of an so-called energy. And we are going to see that pretty soon. Boltzmann machines. We have general adversarial networks, so-called GANs. We have variational autoencoders and many others. So as I said, one of the main reasons why we use Boltzmann machines is simply because we can actually reuse basically everything we had in project number 1. And the only thing we need to do now is to replace the trial wave function. So what we are going to do now is to introduce, if we now look at these Boltzmann machines, and one of the basic things in machine learning is the introduction of the data set, the introduction of a model, and then clearly when you have introduced a model, you need to find a way to assess the quality of the model. And this is normally done by a mathematical function, which is called the cost function or the loss function or the risk function or the error function. The mean squared error is a typical example of such a cost function, which is used to assess the quality of the model. So typically for all machine learning methods, what you have is a data set, and this data set can be fixed, or you can generate new data continuously. So we are not saying anything more about the data set, but this is one of the ingredients. And then we need a model, which we are going to use to reproduce the data which we have. And in our case, the model is going to be given by this Boltzmann machine. And this is essentially the Boltzmann distribution. And then we need a function to assess the quality of the model with respect to the data which we have. So this is normally called a cost or a loss function or risk function, depending on the field where you are, can take different names, but this is the cost function. And this is the function which then is optimized in order to find the optimal parameters. So at the end, after we've done this, then we optimize the cost function. So this will, the model which we have will have a set of parameters, model with parameters. And I'm going to label these parameters with a generic variable theta. So this is the same as the parameter alpha, which we had in the variational Monte Carlo approach in project number 1. But I'm going to label them with a parameter theta here now, just to emphasize that they are not the same as the type of parameters which we used in project number 1. And they were encoded in this variable alpha. So then we would optimize this cost function. And a typical cost function is the root mean squared error. So optimize the cost function. And here we get the family of gradient descent methods, as you did in project number 1. So this pops up again. And with the optimization of the cost functions, then we find the optimal parameters, which then can, in our case, represent the optimal wave function. Find optimal parameters, theta. Now, deep learning methods, and this is something I want just to state. Deep learning methods, they, with at least one hidden layer, there is a fundamental theorem, which is called the universal approximation theorem. With one hidden layer, you can represent any nonlinear function and continuous function to a given precision. So this is a very powerful theorem, which is then used widely to justify the introduction of deep learning methods like neural networks, convolutional neural networks, etc. The theorem doesn't say anything about how many hidden layers you would have, how many nodes you would have in a hidden layer. So what I need to say a little bit now is about the model which we are going to deal with. So in principle, what we are going to have now is a data set. So if we now try still to stay a little bit more generic. So we have a data set X and Y, where X could be some input and Y some output. So what we want then is to represent this data set with a function f x of theta. So we would have a function f, which is going to be given by our model. And in deep learning methods, the model is actually the architecture of a neural network. You could think of you doing some kind of polynomial fitting, then clearly this function f would be a polynomial of some degree, and where the parameters theta would be the parameters of the polynomial expansion. And then you can use methods like least squares to find the optimal parameters, which then reduce the mean squared error. So you would have a data set, and this data set with x and y is then something you want to reproduce with a given model. So this is our model. And then you have a cost function, which is a function of these parameters theta. So this will be a function c of theta, which you then want to optimize. So if you think of an example here, a very famous example, you would have the mean squared error. So that's the mean squared error. So these are just some overarching arguments from machine learning theory. So that means that your cost function would then be given by 1 divided by n, the total number of data you have, and a sum from I equals 0 up to n minus 1. And then you have your data point, which you want to reproduce, minus this function f for a given input x of I as a function of these parameter theta, and this is squared. And this is the function which we want to optimize. So the optimization process is in this case given by an optimal parameter. This is the optimal theta, the one which optimizes this function you've chosen, optimal theta. This is given by the minimization for all parameters which you have, theta element in the set of real numbers up to some dimension length p. So you may have p parameters in your model, and then you want to optimize this function here. And typically then what you do is actually in the optimization process, what you're doing then is to calculate the gradient of this function here as a function of these parameters theta, and you want that to be 0. So this is the kind of overarching view on what you end up doing in machine learning. And if you now think of a neural network, the basics there, what you're going to have is the following type of model. So this is our model now. Just a quick reminder. So you would typically have an input layer, and you would have a set of input data, and these input data from x0, x1, etc., up to some x of n minus 1. These input data, they are represented by so-called nodes or neurons. So you're actually transmitting a signal via a neuron. So this is very much inspired by neuroscience. And then there is a hidden layer. You can have many hidden layers. So there's a hidden layer, and that contains now the definitions of all the parameters which make up your model. So the neural network is the model, and then the neural network has an architecture. And this architecture would now have a set of so-called hidden nodes up to some m minus 1. And all these input points are connected to the hidden nodes. And the connection here is defined in terms of so-called weight parameters, which then form the parameters to be fit. So this x00 connects with this specific node with a parameter. It connects with this other node with a new parameter. We have a 0, 2 here, and this goes all the way. And so all these nodes are fully connected. And this is normally represented by a matrix, which you multiply with the input data, and that gives you a new vector for the output, for the hidden layer. Now, then the next stage is that you have an output layer, which comes in here, and that can also have a set of nodes. So we just call this O0. And the set of nodes, depending on the type of model you have, is going to have a new set of parameters, L-1. And the output nodes are connected with this hidden layer. And then there are so-called activation functions, which produce an output from the hidden layer. And that's fed in to the output layer. And then these nodes produce an output. And that output is then the one which produces this, the values of this function f. So this output, which comes in here, is given by this f of x, and x now is a vector, and theta is also a vector. So every node here has also a parameter which is called a bias parameter, which is normally set to a small number, different from 0. And the reason for that one is that when you train a neural network, you use something which is called the backpropagation algorithm. And the backpropagation algorithm is an algorithm which then needs to be trained with the non-zero input parameters, because the training stops if the weights and the biases are equal to 0. So what you would have then is a set of parameters, which we are going to call for theta. So that will be a collective container for the weights. And I'm writing this as a matrix. So you can think of the input variable being connected with the hidden layers by a matrix times a vector, plus these parameters b. And now I'm not specifying here how many hidden layers I have. So you can make these networks deeper and deeper. And this is something which is the universal approximation theorem does not tell you how many hidden layers you need. It only says that with one given hidden layer, you can represent to a given precision the a continuous function. And the continuous function which we want to represent is obviously this f, which hopefully then represents in the best possible way the data we want to train. So this is the basic structure of a neural network. And there are some key algorithms here. One is the backpropagation, which is essentially automatic differentiation in reverse mode. So I'm just also going to set up automatic differentiation, which is one of my favorite, which is actually one of my favorite algorithms. And automatic differentiation has two modes. One is called the forward mode, and the other one is the reverse mode. So the backpropagation algorithm is the way you train the weights and the biases of a standard neural network. Now, if you look at the standard neural network setup, what happens in our case now is that we cannot use directly what we have from project number 1. We would need some rewrite. There are also some strategic decisions which we have to make. So let me try to illustrate these. So in connection with project number 2, and this is made in order to also make life a little bit simpler for you. So what we want to use is now the Markov chain Monte Carlo, which you had from project 1. We want to reuse the gradient descent, which we had from project number 1. We also want to reuse the Metropolis algorithm with importance sampling. So I'm going to add to this Metropolis Hastings. Alternatively, there is another algorithm which we will discuss next week, which is called Gibbs sampling. So the Metropolis Hastings is actually the algorithm we are going to use now. And then finally, we have blocking for the data analysis. So in order to make life a little bit simpler for you guys, we would like to reuse these elements. Now, if you use a standard neural network, however, what happens then is that we will not be using the Markov chain Monte Carlo. We can or cannot use the Metropolis Hastings algorithm. We would be reusing blocking. We would obviously be reusing the gradient descent method. But for standard neural network, what happens then is that the trial wave function, which we have set up, which we previously wrote in terms of R alpha, this is now going to be a function which will be a function of the parameters R, and we're going to write this in terms of a generic vector X without specifying whether this is a vector or scalar. So when you see an X like this, I'm not specifying immediately whether it's a scalar or a vector or a matrix, but from the context you will see that what is the specific connection. So we are going to rewrite that one, and in a standard neural network, this is going to be replaced with a neural network, which then will depend on these parameters. So this is now the neural network. This is the standard neural network. What this also requires is that we need to bake in things from different neural network libraries. So there is no, how to say, fine-tuned and well-defined C++ library for neural networks. There are actually, but it requires a little bit more labor from your side. So if you think of a C++ code, not optimal, it can be done. It requires a little bit more research. So when I'm saying not optimal, it does not mean that there are not libraries, not optimal for including machine learning, ML, and in our case, these are neural networks libraries. So if we are going to use a standard neural network, the way I'm going to present it when we are done with the Boltzmann machines is to present everything in terms of Python codes. And I'm going to use automatic differentiation. I'm going to use given libraries, and I will present to you how you can implement these libraries. But remember again that the standard neural network path is something which is going to be optional in the project here. If you, on the other hand, look at these so-called generative models like a Boltzmann machine. So in the Boltzmann machine, we're actually going to replace the wave function. This R of alpha is going to be replaced by a new function, which will depend on parameters X, but it will also depend on, so first I'm going to write it like X, but I have to specify a little bit later that it does not only depend on X, but it will also depend on the hidden variables which we have. And there are going to be some parameters. And this function here is actually going to be given by the Boltzmann distribution. So it means that our wave function now is going to be given by a Boltzmann distribution, which I'm going to label as a P of X as a function of theta. And that function is given by 1 divided by a normalization factor, which when we take different ratios and in our actual calculations, we don't need to deal with. And then we have the e to the minus beta. And then there is a so-called energy function of X, which now depends on these parameters theta. So we are going to replace simply the wave function with a Boltzmann distribution. And this energy, or it's a kind of a pseudo energy, this E of X, that is how we are going to model the neural network. So reflects the way we model the network. The benefit here for us now is that we can, if you guys have written everything in C++, we can actually reuse the program which we had. So we can reuse everything we had in project number 1. Project 1 fully, but need to replace the trial wave function, which we had before, this psi with R of alpha, with this Boltzmann distribution. And what we are going to do now, after this kind of more introductory and overarching type of motivation and discussions, we are then going to look into more the details of the calculations here. So the basic thing which I want you to have me with you is that if we look at the Boltzmann machines, which are parts of very popular deep learning methods, and they are so-called generative methods. So they actually allow us to train a given model, which in our case is a probability distribution, in order to reproduce the data. And we can use this probability distribution to generate new data all the time. So the function we want to optimize, now is going to be the same as we had in project number 1. That would also apply to a standard neural network. So the function to optimize is going to be the expectation of value of the energy as a function of these different variational parameters. So what we're going to have then is the same quantity, this E, but now as a function of these parameters theta. That's the one we want to optimize. And then we know that what we end up with is to take the gradient. So we will have the gradient with respect to theta of the energy as a function, the expectation value of the energy as a function of these parameters theta. And we want to drive this one to 0. So we can then reuse the same derivatives of the energy which we had from project number 1. We will reuse the whole Monte Carlo Markov chain machinery. We can then reuse the Metropolis Hastings algorithm. We don't need to introduce any other sampling algorithm. We can reuse the importance sampling, which we have implemented. The only thing which changes now is actually the type of wave function. Now, if you want to solve this in terms of a neural network, then the neural network is the one which then replaces your trial wave function. But in that case, the complication for us, as I said, is that if you have written your code in C++, it will require some extra labor. And again, I have to be careful that this course is actually 10 credits, and it should reflect a certain amount of labor. And in case you're using C++, it may take a little bit more time, but if you're dealing with Python, this is much simpler. So the examples which we will have in the lectures, they will actually use a Python library. Samples in lecture in Python. Now, I assume that many of you have written in C++, and I've seen that from the reports. So, and that is why we would like to focus on Boltzmann machines as the kind of standard methods for getting started. So what I want to give you now are more the details of what we are going to look at. So the basics of a Boltzmann machine, we are going to look at something which is called a restricted or reduced Boltzmann machines. And this is normally shortened to an RBM. This is a system where we are going to have a set of input nodes, which now represents the variables of the different particles we have. So we will have a set of input nodes, x1, x2, etc., up to some x of n. So this is going to reflect the dimensionality of the system and the number of particles, because these x's are going to represent the positions of the particles. Now we are going to have some hidden nodes here, and these hidden nodes are connected with the input layer or the visible layer. So this part is called the visible layer, and visible because this is the part we are interested in. And this is called the hidden layer. And all these are connected. So every input node is connected with the hidden nodes. And I'm just going to put dots here to indicate the connections without messing up too much the graph here. And this connection is given by a weight function, W. Each node here is going to have a bias. So it means that when I look at the parameters I have, there's going to be a connection between an xi. There will be a matrix elements, wij, which then connects with a hidden node, hoj. There's going to be a bias parameter, which connects with the input layers. And this is often done then to avoid in the case where the W's are equal to 0 by accident, because that will normally stop the training. So these are called bias values. These are going to be the weights. And finally, we are going to have a new set of parameters, C, which then link with the hidden layers. So these are also going to be the biases. And the total set of parameters now are going to be given by these parameters B, C, and W. These are the parameters which we want to optimize in a standard optimization algorithm. So that means that we need to do some kind of gradient descent in order to find the gradients and optimize the gradients. Now, the trial wave function, as I said, is going to be represented by a Boltzmann distribution. So what we are going to have now is that the trial wave function, and we can decide now if we want to use a quantum mechanical approach, where the trial wave function then has to be the square root of the distribution, or whether we let the wave function be equal to the Boltzmann distribution. So the standard approach is actually to let the wave function be the square root of the distribution. But let's just write in a more sloppy way this wave function now, which is being replaced by this Boltzmann distribution, which now depends on xh, so the hidden nodes, and the input variables. So we actually have to get rid of the input variables, the hidden layers. And this brings us back to some properties of distributions. So before we take a break, let me now write out this x of h of theta. So this is going to be given by the Boltzmann distribution, where we have a normalization constant. And then we multiply this with a function which I call tilde of x of h, and these parameters theta. And this p tilde here of x of h of theta is going to be given by the exponential minus beta, and we would put the temperature equal to 1. And this contains now an energy function, which we are free to model as we want. And we are coming back to that after the break. And this quantity z is now equal to simply the sum over all possible configurations you can have. So I'm just going to write this as a sum over x and h without specifying properly what they are. And this is simply going to be given by this probability which we have here, or this function p tilde. And this function as a normalization factor. Now, after the break, we are going to define some quantities which are called marginal distributions, because when we are going to look at the final wave function, we are not interested in the hidden layers. We are actually only interested in the visible layer. So that means that we would have to sum away the hidden layers, or if this is a continuous distribution, we would have to integrate away the hidden layers. But the basic recipe here is that we are going to replace the trial wave function with a probability distribution. And in the implementations which we have, we are going to replace that one with either the wave function to be the probability distribution, or the wave function to be the square root of the probability distribution, which is the more correct way if you think of quantum mechanics, where the wave function squared defines a probability distribution. So this type of approach is going to make it easier to get started with a deep learning method, and in particular, in our case, with Boltzmann machines, because there we can reuse everything we had in project number one. And the program example, which I'm going to show you, is an example of how you can actually get started rather quickly with implementing Boltzmann machines. When it comes to neural networks, this requires a little rewriting. It's not so much, but the Boltzmann machines are the most immediate ones, which we can implement without too much pain. So I hope you see the pedagogical reasons for why we focus on Boltzmann machines. Boltzmann machines are also part of a very, very active area of research in machine learning. And these are called the generative methods. And they are extremely useful and extremely popular when it comes to unsupervised learning, which is perhaps, and this is my own bias, the more interesting part of this kind of learning methods. If you have supervised learning, these are methods which often are very labor intensive, in the sense that you actually need somebody who labels the data and classifies the data for you. Whereas these generative methods, they are applied to unsupervised learning where you don't have labeled data. And there is a lot of data from, in particular, physics, both theory and experiments in particular, where you have tons of data and you're not able to label all the data because it would be way too expensive. So generative models, like Boltzmann machines, are interesting per se. They also, for us, they form a pedagogical lower threshold for getting started with project number 2 and implement deep learning methods. And we can reuse everything we did in project number 1. And we need simply to replace the trial wave function with a Boltzmann machine. Secondly, if we want to use standard neural networks, we need to labor a little bit more. And we would also have to introduce more tailor-made libraries, which are often interfaced in Python, which means that if you have written your code in C++, there can be a higher threshold for getting started. So there are several reasons for why we opt for the Boltzmann machines. So after the break, I actually wanted to look more into the mathematics of Boltzmann machines so that you see how you can implement these methods. So I went a little bit over time, but that was deliberate because I wanted to give you this kind of more overarching arguments. And then after the break, we are going to go a little bit more into the details so that you see the wood for the trees here. And we will also use parts of the next lecture to complete the discussion of the mathematical details. So I'm going to put the recording on pause now. Now, the basic philosophy, as I said, of these Boltzmann machines is that we are going to represent the trial wave function with a probability distribution, which is given by a Boltzmann distribution. So in that sense, we are pretty free to model this function E or which is normally called the energy, as we want. So everything which we are going to do now resides in our capability to model this specific function which you see here. So you can now think of this function here as the one which contains the ansatz for the wave function. And the thing is that this function does not need to reflect the physics which we have incorporated in, like in project number one. So in project number one, we actually baked in our knowledge about the harmonic oscillator when we set up the trial wave function. Also, when we set up the correlated part of the wave function, what we can do then is to bake in a lot of the physics which we have. Now, you can take a kind of agnostic view and say that you're not very much interested in the basic physics, and simply let's see what a parameterization gives us. Now, for these specific functions which we have here, this E, there are many, many options. In general, this will be a function of the various parameters x and h. And one option is that x and h take binary values. So that means it could be -1 or +1. In case you're dealing with spin systems, this is actually very interesting as an approximation. So this is normally called a binary-binary. Binary-binary simply means that x and h take binary values. And as I said, if you're dealing with this kind of spin Hamiltonians like the Heisenberg model or the Ising model, this is actually very useful. So in that particular case, it means that this function, this x of h of theta, is now simply going to be given when we spell out all the parameters. It's going to contain a sum over all the visible nodes. So let's call this n, the number of visible nodes. And there's going to be a parameter, a, we actually call this parameter for b. So let's be consistent. A parameter b of I, which is then multiplied with a given value for x. And in this case, it could be -1 +1, 0, 1, depending on the system you're looking at. Then there is a sum over all the hidden nodes, m-1. And then we would have this parameter c. And this is then multiplied with the value which this hidden node takes. And then finally, we have a so-called interaction term where we let the nodes for the visible layer be connected with the nodes in the hidden layer. So you could actually think of this as some kind of interaction between the hidden layers and the visible layer. So this obviously is a double sum over I and j, and then we would have a sum up to n-1 and m-1, and then we have a xi multiplied with these parameters wij, these are the weights, and then multiplied with h of j. So this is a very popular model. Now, in our case, we are interested in not the wave function as a function of x and h, but we are interested in the function of x as a function of theta, which is now going to be given by this Boltzmann distribution of p of x of theta. This is, however, something which we call a marginal distribution. So that means that we need to integrate or sum away the hidden degrees of freedom. One way to think of these hidden degrees of freedom is actually some kind of hidden latent variables, which are just used as a kind of crutch to give us a more flexibility in parameterizing the results. So that means that this quantity p of x of theta is actually going to be a sum over h, and in case h are discrete values. And then I would simply now sum over x of h of theta. So I would sum up these specific variables, and you will see below here that when we are setting up the final trial wave function, we actually need to calculate this marginal distribution. So just keep that in mind. This is a technicality. And this technicality is also important for us because it goes back to the type of approximation we choose here. Because some of these approximations are actually going to give us analytical results, which are easier to program when we calculate this quantity. So we have some flexibility in choosing the type of energy function, and this energy function does not need to be well linked with the physical system which we have. You can just think of this as generating one specific model, which we then, where we obtain the parameters through the optimization, which basically means calculating a gradient. So we are interested in that. We have other types of distribution functions or energy functions. And one which we are going to implement is a so-called Gaussian binary. We can have a Gaussian if we want to. So a Gaussian binary means that this function x of h and the parameters theta is going to be given by a sum of I equals 0 up to n minus 1. And then we are going to have x of I minus some parameter b of I squared. So this mimics what we would have in a Gaussian. And remember now, it's called Gaussian binary because we have the exponential of this energy as the final function which we're looking at. Now, there could be parameters here. So if in case you have the standard deviation of this parameter x of I, in case you know that, you can calculate the variance. But often, since you don't know this quantity, you would just put that one to 1. And then there is the binary case, which now kicks in for the hidden nodes. So this is an m minus 1. And then we would have this parameter cj times hj plus the final one, which now links the hidden layers with the visible layer. So we would then have an x of I, and then we would have the weights to be trained by the gradient descent method. And then we have the h of j here. You can have Gaussian, you can have more complicated ones. But the reason why these two types of models for the energy function are used is that we can actually calculate the marginal distribution, which you have here, this quantity, which we then need to define the final wave function, because the final wave function will not depend on the hidden variables. So the only parameter we are interested in is a wave function which takes as input a value x. Any questions so far? So keep this as it is. It is just a model which we're making up. And when people are training these type of models, you're often looking after functions, which in our case is the probability distribution, which is as simple as possible. And perhaps we can even calculate analytically the so-called marginal distribution. And that simplifies the calculations. And you will see in many of the gritty, nitty details in the Jupyter notebook for today, you will actually find the derivations of these marginal probabilities. Now, but before we do quantum mechanics at all, let's just look at the type of complications which you would have when you take this function P, the probability distribution. So what we want now is to assume that this probability is the one which defines our data. So assume now that we have performed an integration or summation. So if it's a discrete function, we would sum. If it is a continuous function, we would integrate over h. So it means that you would actually have an integral over h defined in its domain, and then you would have a p of x of h as a function of theta, and then you would have an integral over d of h. So we integrate away those degrees of freedom which we cannot relate to some observable. And in our case, we want to have a probability distribution which describes the data. So keep that in mind. Yeah? So assume now that we have this px as a function of theta. So we've integrated away h, and this function is nothing but, as we said, the partition function which now has also integrated or summed away the x values. So this depends only on theta now at the end. And this is then multiplied by this function, which we call x tilde here. And this x tilde, p tilde is actually, so let's just quickly repeat that and see where we can meet the bottlenecks. And we are going to now, later, we are going to actually show what is going to be the cost function which you need to optimize. So this px of tilde, just to remind you what we said, is going to be equal to minus beta times this energy, where we now have integrated away the hidden layers. And the partition function is actually going to be given by the sum of all the x's of this p of x of theta. And normally we would put beta, which is in statistical mechanics is Boltzmann's constant divided by t. We're going to put that one equal to 1. So we are not interested in that parameter. So we are not going to fine-tune that parameter. Remember also that there is nothing which hinders you now. When you look at the ansatz we are going to make a little bit later, where we are going to replace the trial wave function with this Boltzmann distribution, there's nothing which hinders us now to actually multiply this Boltzmann distribution with some additional functions. So this could be functions which we know have to be there in order to satisfy some minimal requirements on the wave function. So there's nothing which hinders us from doing that. And that could be us multiplying this Boltzmann machine, which gives us some flexibility in handling unknown parameters. And we could multiply that one with a wave function which contains relevant physics, like the correlated part of the wave function. Now, when we now want to optimize and find these parameters, so we could assume now that this p is our cost function. This is the function we want to optimize. So we want to optimize, and this is one of the basic ways of dealing with this problem. We want to optimize this probability p of x of theta so that it reproduces in the best possible way the data. So you could think of p as our cost function. Now, since this function p is going to depend on exponentials, it's actually better to optimize. Instead of optimizing p here, we could actually optimize log. And depending on whether we want to minimize or optimize, we could maximize or minimize. We could then choose the negative log or the positive log. So let's take the positive log now, because that means we have a maximization problem. So we are going to deal with that. If we want to optimize that function, what we need then is to calculate the gradient. And as I said, I'm skipping vector signs, and it should be obvious that this gradient is actually an object which applies to all the parameters we have. So all the weights, wij's, the biases, etc., and other parameters. So what we want to optimize is this function here now. So p of x of theta. And we want that one to be equal to 0. And you see now that if you use the definitions which we have, this is something which can be pretty delicate when we are dealing with the probability distribution. Now, in our case, we will not deal with the probability distribution, but we will deal with the energy of the system. And that makes life a little bit easier. But the general Boltzmann machine requires you to be able to evaluate the normalization factor. And the normalization factor here, which is called the partition function, for those of you who know statistical mechanics, this function here is actually basically impossible to calculate because you have an infinity often of these x's. And it's a multidimensional object. This quantity here is also a multidimensional object, but hopefully we can draw samples from that without a too high computational cost. But basically what we want now is to optimize this function here by calculating the gradients. And I just wanted to give you some of the basics of Boltzmann machines. But then for our own practical needs, we are not going to optimize what you see here. Our cost function is going to be the expectation value of the energy as a function of these new variational parameters, which are given by the Boltzmann distribution. But if we take the standard path, if you look at this equation here, this is going to be equal to the gradient. And then I'm going to have the gradient of this log of p tilde of x of theta. And we have assumed now that we have integrated away the hidden layers, because this is the quantity which is of interest to us, and that's the quantity we want to optimize. We are not interested in the hidden parameters, but the hidden parameters are actually included here because these functions are defined in terms of an integral or summation over the hidden layers. And then we have a minus of delta of theta. And what we end up with is to calculate the log of the partition function as a function of theta. And you can see that immediately from the basic mathematical form which we have. I'm simply taking the log of this function here. And the benefit of having this in terms of an exponential form is something which will become clear now, the benefit for that. So let me just proceed a little bit. So the problem is obviously the calculation of the partition function, which we still have to deal with. The first term is called the positive phase. And if you deal with this as a minimization problem, the signs are inverted. So the first term would then be the negative term, and the second term would be the negative phase. So these are just names which you will encounter both in my slides and also in the standard literature. So the problem which we have is actually the calculation of this quantity here, because that requires the calculation of the partition function, and we don't want that. So this is something we quickly see is now given by the derivative of c of theta divided by z. And I'm just skipping the theta. I'm going to skip the theta dependence here. If we then look at the definition which we had, this is now going to be given by the derivative. And now I have the sum over all the x's here. And this is p of x of theta. And this is again divided by z here. So we assume now that we, if this has been an integral, we would have now an integral over x. And we assume now that these are continuous and differentiable functions. So we can actually take the differentiation inside the sum or inside the integration sign if it's a continuous distribution. And this is, for those of you who remember some mathematics, it's called the Leibniz rule for differentiation under the integral. So we can then rewrite this one as a sum over x. And then we would have a derivative of this probability distribution of x. So that, let me just, this should actually be given by this probability here. Just let me just remind you, so it doesn't have that one like this. I just need to be a little bit careful with my notations here. So this would now be given by the sum over the x's, and then I take the gradient of this probability distribution which I have, which is now unnormalized, and then divided by z here. And if I look at that one, this is something which I can modify. There's a very important property as well, and that is that this p of x of theta being given by an exponential is always larger than 0. That's also very important. It can be infinitesimally small, but it is always larger than 0. That's also another important property in the method behind what we are doing now. So if you look at this p of x, this is something which we can obviously substitute with the exponential of log of p of x. So I've skipped here the theta variable just for the sake of simplicity. So what we get then is that we can now rewrite this sum here as a sum over the gradients of the exponential of the log of this function p tilde of x of theta and divided with a partition function. And if I look at that one, if I take the derivative of this function here, this is nothing but the sum over x. And then I have the exponential of log, and this is the benefit of also this type of functions which go like exponentials, because you will see now that this simplifies considerably. And then I have multiplied with the derivative or the gradient of log of p tilde and divided by z. So if I look more carefully at that one, this is going to be simply the sum over x. So the term which we have here, this one, this simplifies simply to p tilde. So I get the p tilde of x as a function of theta and multiplied with the derivative, the gradient actually, of log of p tilde of x of theta. And this is divided by z here. Now, what this actually is it's actually pretty interesting for us, because we know that if I take p of x of theta divided by z of theta, this is nothing but the probability distribution which we had, px of theta. So we can actually rewrite that function which you see here as a sum over x, and then I have my probability distribution, which is now normalized as well, multiplied with a function here. So this is log p of tilde of x of theta. Now, this log function, which you see here, the gradient of that one, since we now are multiplying this with a probability, if you now think of the standard expectation value of a given quantity, let's say a quantity f, this is simply to some power n. This is simply now given by x, and then px of theta multiplied with this function to the power of theta, now power of n of x of theta. So this is just the expectation value. So this e with a double bar here is the expectation value. So what you see now is that the function which we have written out here is nothing but the expectation value of the quantity of delta t of log of p of x of theta. So what we have now is actually us being able to compute the gradient by approximating the calculation of the partition function. So originally we started with the partition function here. We had to have the log of z, and we can actually rewrite that one in terms of this function here, which now is the same as delta t, delta theta of log of z. Still, we need to calculate these derivatives, and that can be involved, but this is something which is doable. So when you're dealing with a standard Boltzmann machine, and we are not thinking of another cost function, this is actually what you would optimize. And the literature is full of discussions on how you actually optimize the partition function. There are tons of ways of doing that. And the kind of ways of doing that is something which you can find more about in the lecture notes which we have. So let me now switch back to the Jupyter notebook, because what I wanted to give you is the kind of overarching view of what you need to program. So what I gave you here was just a basic overview of how you would typically set up the optimization of a Boltzmann machine. And where the idea now is to optimize a probability distribution in order to reproduce a data set, which you are dealing with. So the thing with the Boltzmann machines is that you have a lot of flexibility in defining this function E. When we are going to quantum mechanics, we have to be careful with that function E, because we would need that function to respect some specific symmetries. But in general, the method is very flexible, and what you would put in this function, whether you have a binary Gaussian binary or other methods is something which depends on your specific application. The other thing which I want you to keep in mind is that when you're calculating your final probability distribution, you want the probability as a function of x only, which are your visible parameters of x and the parameters theta. And you want to find the optimal parameters. So by requiring that the gradient of the probability distribution, in this case is 0, is something which will give you the optimal parameters. Now, what you then want in the specific implementations is to have a function here, this function E, which now has integrated away the visible layer. And the reason for choosing Gaussian binary or Gaussian or binary is that you get a analytical expression for what we called here the marginal probability. So I hope you can see the wood for the trees. So we have a marginal probability, which is going to define our trial wave function. And we want this to be something which can be easily calculated and at the same time be meaningful in a statistical optimization process. So to recapitulate, we want to reuse our Markov Monte Carlo chain. We want to use the Metropolis Hastings algorithm. We want to use the gradient descent, all these ingredients which we derived in project number 1. And at the same time, we now need to optimize a function here. And the function we are going to optimize is not the probability distribution per se, but we are going to use that probability distribution to define the trial wave function. And that means that we are going to optimize the energy. And that means that we are going to use the same functions which we defined in project number 1. So if we now replace a Boltzmann machine with a neural network, we are going to see much of the same, except that then if you use a neural network, it's less easy from a computational point of view to integrate the automatic differentiation and backpropagation in your C++ code. If you're willing to write everything in Python, then obviously life is easier because you can actually use Python libraries for like TensorFlow or PyTorch or similar ones, if you're familiar with those, to perform the optimization. I'm actually going to give you access to a software which allows you to do this in case you want to implement a neural network. But from a pedagogical point of view, and also as a function of the timeline with our deadlines, etc., the Boltzmann machines are the easiest ways to implement machine learning methods in project number 2. And secondly, it also gives you an insight into widely used methods for unsupervised learning. Any questions so far? Because I want to spend the last few minutes on showing you the program which we have in today's Jupyter Notebook. And then next week, I'm going back to some of the technical details. So I'm going to keep this kind of a top-down approach today, and then give you all the gritty details are in the slides. But what I want to do now is to condense out what you need to do. Okay, so I'm going to switch back to the, is everything clear? So there are many small details here, right? So I'm just trying to step you through in small steps through the basic details. And it's important that you have this kind of overarching view of the pros and cons of the different methods. Now, I should also say that these Boltzmann machines are less flexible than a neural network. So there was a lot of hype in 2017 when the first calculations were done. But then, since you have less flexibility in the design of the energy, that means that in the design of the trial wave function, you are a little bit more locked with a Boltzmann machine, because it depends very much on your ability to calculate the marginal probability. And you want this marginal probability to be a simple to use analytical expression, but that can take away some of the interesting physics. And if you're going into modern research, then it's the usage of neural networks, which really has created a kind of revolution. But we have also to keep in mind, oh, that's my job, that this is a 10-credit course. There are some balances which we have to strike. Okay, so let's go back to the Jupyter Notebook. And in the Jupyter Notebook, you will find many of these details which we have discussed till now. But what I want to do now is actually to guide you to the end of the slides. And then next week, so it contains also kind of reading recommendation for next week. I am going to look more into the mathematical details. The mathematical details are here, but I will not go through them now. But you will need to go through them and read them in order to understand how I actually have implemented this Boltzmann machine. So in the beginning here, you will find the standard or generic description of a Boltzmann machine. And this contains basically what we discussed now on the whiteboard. We went through this Gaussian binary, etc., etc. There are many other types of functions. We went through the calculation of the cost function, where we actually now optimize this probability distribution. So this is essentially what we put on the whiteboard. And the optimization and the training is typically done with, let's say, a gradient descent or stochastic gradient descent, which many of you are familiar with. So we don't need to spend more time on that because we have already discussed this in connection with project number 2. So that means that you would end up with some optimization here. And the way you would typically calculate this log of the partition function is then by calculating the log of this energy function, or the probability, or this function p tilde as we defined in the whiteboard. But I want to scroll down here, and then we are coming back to many of these details next week. But what you will find is actually with a given type of Boltzmann machine, like this one, you would now calculate the marginal probabilities, and these are the quantities which will define your wave function. So depending on the type of Boltzmann machine you have, you will have to evaluate these integrals. So the slides here contain these kind of gritty-nitty details on what you need to calculate. And you will also need for the probability for the hidden layers. So there are lots of details which I want to cover more closely next week. And the typical Boltzmann machines are the binary, this is BB. And in this case, we calculate the marginal distributions. So I've gone through the mathematics here. It's not that exciting, but these are the final results which we typically end up using. And you will also get the marginal distribution for the hidden layers. And then you can set up, the conditional probabilities. And these are just technicalities. And I will go through this more in detail next week so that you see how you get to these expressions. And then we have a Gaussian binary, which is the one which is implemented in the code below here. You need to calculate these different probabilities. You want to have the marginal probabilities because this is going to be your final probability. And then you need to integrate away these different variables. And I'm coming back to that. So if you then scroll down, in order to stay with this kind of, so there's a lot of details here which are not so exciting. What we are going to do now, and this is to define actually the wave function in terms of this Boltzmann machine. And it's going to be given first in terms of X and the visible layers. No, the visible layers and the hidden layers. And if we do that, we could define the trial wave function to be the marginal probability where we integrate or sum away this quantity. And that gives us, when we do the mathematics here, and this is something I will do in more detail next week, Or alternatively, is actually to use the physical definition of or the quantum mechanical definition of a probability distribution, which is the wave function squared. And this is going to be given by this Boltzmann machine. So that means that we are going to have a trial wave function, which is going to be given by the square roots of these quantities. And what you will see then when you do the mathematics is it's just going to give us a factor, since we are going to take logs here at the end. It's just going to give us a factor of a half. So I would like you to read through some of these details. And the cost function now is not going to be what I put on the whiteboard, the probability distribution, but it's going to be this quantity here, which you have seen before. So we are going to calculate this object. And that means that we can reuse everything we had before. The only difference now is that psi is going to be a Boltzmann machine. And you can make it more complicated, but you see now the benefit of using the Boltzmann machines is that in the training, in the optimization here, we can now use everything we did in project 1, except that now we are going to have more parameters. And these parameters will be given by the biases and the weights of the Boltzmann machine. So that's the basic difference with what you did in project 1. So it means that you can reuse everything. If you are going to replace this with a neural network, then we have to be a little bit more careful and rewrite the code a little bit. And we will come back to that. And that's why I say this is optional, because that would require a little bit more labor. That means that when we calculate the derivatives here, we can reuse the same trick which we did in project 1, and then simply realize that this is the log of psi. And if I use my Boltzmann machine, this is the log of the partition function, and then I have the Boltzmann machine here with these probability distributions, the marginal distributions, which we set up. This gives us different derivatives. So we have the biases, we have to calculate that. We have to calculate the derivative of the biases of the hidden layer, and then we have the derivative of the weights. So when we are calculating the derivatives now for these different quantities, we now need these quantities which you see here. And the only difference if we take the square root compared with not taking the square root is a factor of a half. And that results in these equations, and these are the equations which we need to code when we take the derivatives. So our Hamiltonian could be this, and this is the example which you will find below and which we're also dealing with in project number 2. Then the quantity we want to optimize is the expectation value of the energy. So let me see. So this is correct. There's I have not tried these libraries for automatic differentiation. I have tried a library in C++, which is called AutoDiff, which is a precursor to that. So as I said, there's a main pedagogical and time reason for why we normally recommend Boltzmann machines instead of neural networks as a first step to get familiar with this machine learning way of thinking, is that it's much more straightforward to actually implement this trial wave function compared to what you would if you have a neural network. So if you wish to use your C++ functions, there is a little bit more labor to do that. But we will discuss that next week and the week thereafter. But what I list here is a series of derivatives which you need to plug in. So this would actually be the expectation value of your energy. And the code which you see down here actually sets up these different expectation values. And it says my time is running out. So I invite you to take a look at this now in connection with the project. And next week, I will go through the mathematics. So what I'm doing here is actually to plug in as a wave function these Boltzmann machines. And then I'm calculating the local energy as before. I can do it with and without interaction. You will see with interaction, the results are not going to be too good with adjusted Boltzmann machines. But this case here, when you run this for just the harmonic oscillator in 2 dimensions and 2 particles, you should get 2 here. And you will then see that what I'm doing now is simply to reuse everything we did in project number 1. And you will see now that the energy gets pretty close to 2 here as a function of different iterations. And the iterations are done by the same function which we had in project number 1. I calculate the energy derivatives. I have my gradient for the biases and the gradient for the weights, as you can see here. And these are the quantities which I then plug in and multiply with the learning rate. So this is the simplest possible gradient descent method which we can have. And I'm running through 50 iterations. My eta is 10 to the minus 3. And the function which you see here are essentially the same functions which we discussed in project number 1 and which I presented in terms of Python functions and which you have programmed in either C++ or Python. And somebody has done it in Julia as well. So the basic metropolis sampling, the Green's function, etc., they are included here. And the only thing which changes is actually the trial wave function, and which now is defined in terms of these Boltzmann machines, or this Boltzmann distribution, which is more correct to say. So what I want to do now is to simply give you a small assignment. Take a look at the derivations which you have here. And then next week, we are going to go through some of these details and discuss in more detail how we can move on with Boltzmann machines, and then start looking at the implementations of neural networks. So I hope you can see the pedagogical approach which I thought we could use here, which gives a kind of almost minimal change to what you have done. Any questions so far? Things which are unclear? So the kind of homework is actually now, both during the lab sessions and till next time, is actually to go through those notes on Boltzmann machines and how you calculate the marginal distributions, which then define the trial wave function. So think of this as just somebody who gives you a probability distribution and then says, optimize this distribution to get the best energy. So for the harmonic oscillator, when I use the Gaussian binary, actually the harmonic oscillator goes like x squared. So having this Gaussian binary is the reason why I'm getting the harmonic oscillator energy so well. When I include the interaction term, you will see that that is not going to give as good result as you would get with a standard variation of Monte Carlo, where you have added a correlated part to the wave function. We will discuss this in more detail next week as well. But it's so the Boltzmann machines and these generative models, they use all this machinery of Markov chain Monte Carlo. And the sampling rule can be Gibbs sampling, or it can be the standard Metropolis Hastings, which we have been using. So I hope you see the woods for the trees here. Eh? That's the, and also some of the pedagogical reason for why we implement this specific approach. So you can think of that as an entry point to studying deep learning methods applied to solutions of quantum mechanical problems. Because when you have the expectation value of the energy and you take and you optimize that one, the next step is actually to include a neural network and replace the Boltzmann machine with a standard neural network. And that's going to give us more flexibility, actually, much more flexibility, because with a Boltzmann machine, we would have to recalculate again and again the different marginal probabilities, depending on the ansatz we have for the function, the energy function E.
All right, thanks, Morten.
Yeah.